the special slash very important case. So this happens when our y sub 1 function and our y sub 2 functions, which are solutions, so when they are both solutions to an ODE, and specifically a second order ODE, okay, because that's what we're dealing with, and, this is the important part, and are linearly independent. Linearly independent. Okay, so big question. Alright, so we know what it means to be solutions to an ODE, right? That just means if you plug in y sub 1 into the equation, then it'll satisfy it, and if you plug in y sub 2 into that equation, it'll also satisfy it. So that's what it means to be a solution to an ODE. But we don't know what is linearly independent. What the heck is that? So let's define that. So in order to be linearly independent, I'll just abbreviate with this, okay? So that means independent. Linearly independent functions, let's use some other variables just for demonstration. Let's say u and v, okay? So these are two random functions, and they're linearly independent. They're linearly independent if neither are, or is, if neither is a constant multiple of the other. Okay, and we'll explore how to determine this linear independence. Okay, and then also, so this is one definition of linear independence. Okay, and another tool you could use is called the Wronskian. Okay, so let me write it here, Wronskian. So this is another tool to determine linear independence or not. Okay, so determine whether two functions are linear or not. So to determine linear independence. Okay, and let me show you how that works. So the Wronskian is basically, let's say we're given our functions, right, u and v. So we have a u of t and a v of t. Okay, so those are two functions here, and the Wronskian between them is denoted by capital W. This is equal to the determinant of something specific. So we're just going to stick both of these guys in here at the top row. So u of t and v of t, and right below them, their entries are the first derivative of each of these functions, okay? So u prime and v prime, basically. And how to calculate the determinant, you basically just take the first, the product of the first diagonal here. So that would be u of t times v prime of t, and then you subtract away the product between the other two entries, so these ones here. Okay, so that would be u prime of t times v of t, okay? So now that we have this is the Wronskian, that's what it's called, okay? So then we have if our w of t, if this whole thing ends up equaling 0, then that means that this means that u and v are linearly dependent on each other, okay? Linearly dependent. So I'll just write dependent here. Okay, and then if not, so then the other case is if our w of t, if our Wronskian is not equal to 0, then that means that u and v are linearly independent. Okay? So that's how we could use the Wronskian, like I said, as a tool to determine linear independence. You just set up, given your two functions, you just set up this determinant thing here, you calculate that and see if it equals 0, then that means that our two functions are linearly dependent on each other, which would also mean they're constant multiples of each other, right, using this definition up here. But if we have that the Wronskian is not equal to 0, that means u and v are linearly independent, therefore they're not. Neither of them is a constant multiple of the other. Okay, so here's like method 1, I guess you could say, and then here's like method 2 to determine your linear independence of two functions or not. Okay? Alright, so let's go back to that special case. So back to the special case. When we have, so let's say y sub 1 and y sub 2 are both solutions to our ODE, okay? Both solutions to a second order ODE, And we're going to say, and they are linearly independent. I'll just abbreviate. Li means linearly independent. Okay? And they're linearly independent, whichever way we determine this, either using the Wronskian or determine that neither is a constant multiple of the other, which I'll show you how to do in a practice problem. So if we have both of these are true, then we have they as in y sub 1 and y sub 2 form what's called I'll put it in parentheses, fundamental set of solutions. Okay? That sounds really important, right? So what does this mean? So a fundamental set of solutions means, and usually it's written something like this in fancy curly brackets here, so you could write something like this, right? So something like that. So each of these entries, by what a fundamental set of solutions means is that you can, from these entries or from whatever is in the set, you can form all of your solutions to an ODE in this case. You can form all of your solutions just by taking linear combinations of these two entries here, okay? And if you did have a fundamental set of solutions that had 3 entries per se, then you could form all of your solutions by taking linear combinations of those 3 entries as well. So in this case, we just have the 2. So this means that we can form a general solution. Then our general solution, which composes all of the possible solutions to our ODE, our second order ODE, then the general solution, y of t, could be formed using the following. So y of t is just going to appear as a linear combination of our of the components in the entries in our fundamental set. Okay, so this will be like saying c1 times y sub 1 of t plus c2 times y sub 2 of t. And again, this is what's called a linear combination, right? Because we multiplied each by a constant, like that, and then we just added them together. Okay, so this is our general solution to our ODE, given that y sub 1, again, important note, y sub 1 and y sub 2 are both solutions on their own, and they are linearly independent of each other. Okay? Alrighty, and there we have it, our general solution, which again, once more, contains all of the possible solutions to our ODE. Okay?